Unit 14, 36 to 39. Please take a look. Okay, so let's look at Unit 14, questions 36 to 39. Okay, so a pair of structural isomers, looking for a pair of structural isomers, you know, for those of you who've done biomed, holy cow, if you got this one wrong, you've got to go back and do biomed again. Because of course the conversion from glucose to fructose in our metabolic pathway is using an enzyme called isomerase. So that's a hint and a half, because enzymes usually have names for what they do, and so it's called phosphate hexose isomerase. But the point is, it's an isomerase, which of course, enzymes are biological catalysts that produce the activation energy of reactions, and so this one is a reaction to make an isomer of each other. But in terms of what you need to be able to do during the exam is you need to be able to look at your first answer choice, glucose. Well, first of all, you need to know what an isomer is, and as we've discussed, an isomer has the same molecular formula, so it has the same number of atoms. It's just that there is a different arrangement. That is what an isomer is. Now there's two big categories of isomers, as I mentioned before, and one is the structural, also called constitutional isomers, which means there's a different connectivity, the bonds or the arrangement or whatever, different connectivity. Whereas there's stereoisomers, which is a change in the three-dimensional shape, and there will be questions on both to do with it. This is about structural isomerism. So we look at glucose and fructose, and the first thing we want to know is, do they have the same atoms? Do they have the same number of atoms? And if you count your carbons, you see that there are 6 carbons. You should count the hydrogens. There's 12 hydrogens, and there's 6 oxygens. And it's the same in both. And in fact, this is why carbohydrates are called carbohydrates. You see that there are 6 carbons, but then you see there are 6 waters in this molecule. So it's a carbo-water molecule. It's a carbohydrate. 6 carbons and 6 waters, because it's H2O times 6 in this molecule. So glucose and fructose, definitely structural isomers, as you can see there. Let's, for fun, look at citric acid in the not the mechanism, but in the graph or scale figure provided. Citric acid going from citric acid to oxalosuccinic acid. And when you look at that, clearly, in fact, they could ask you the following question: what type of reaction is occurring when you go from citric acid to oxalosuccinic acid? They could ask you that. That is a legitimate GAMSAT question. Is it hydration, hydrolysis, reduction, oxidation, nucleophilic substitution, third order? They wouldn't ask that last one because it doesn't exist. But basically, what type of reaction is occurring in answer choice B? Well, in organic chemistry, we say, and you get this from that link I gave you earlier for the organic chemistry mechanisms. I talk about that in that video, is that once you increase the oxygen content of a molecule, or you remove hydrogens, that's called oxidation. If you add hydrogens, or you remove oxygen, that's called reduction. So answer choice B is an oxidation reaction. It's a reaction. There's a removal of atoms, and the fact that you remove 2 hydrogens means that it cannot be an isomer. Isomers must have the same formula. There's no change. So let's quickly look at fumaric acid going to oxaloacetic acid. So the quick and easy thing you can see is that there is a double bonded oxygen, which is different. And so there's a difference in the atoms. It's not just an issue of connectivity, which is also different, but there's a difference in the number of atoms. And, okay, and then oxalosuccinic acid, oxaloacetic acid. Wow, lots of changes, you know, COOH, the whole COOH group is missing. So there's lots of changes there. But A has no change, changes in the number and types of atoms. So the same number and types of atoms, same molecular formula, isomer. And so we've identified 36, answer choice A. So 37, two compounds that have the same empirical formula. So you know what a molecular formula is. You know what a molecular formula is. H2O, H2SO4, you know, and for glucose and fructose, C6H12O6. We just saw that. C6H12O6. Those are molecular formulas. But empirical formulas refers to the simplest whole number ratio of the atoms in a molecule. So for glucose and fructose, C6H12O6 is the molecular formula, but you can see each one of those numbers is divisible by 6. So CH2O, which is carbohydrate, carbon, water, CH2O is the empirical formula, the simplest way to show the relationship numbers. So now when we look at two compounds that have the same empirical formula, we look at answer choice A, so fructose, I just said it's CH2O, is the empirical formula. Now we need to see what about succinic acid. So succinic acid, we count up the carbons, we count up the hydrogens, count up the oxygens for succinic acid, and this is question 37. And for succinic acid, we get C4H6 4. So I think everybody gets that. C4H6O4. And so the empirical formula would be what is the lowest number that we can divide all that by. So that W2, and then we get C2H3. It's like trying to find a common denominator, that kind of thing. So it's C2H3O2. Yeah. So that would be the empirical formula, which is clearly different from fructose, which is CH2O, which I've already mentioned. Now looking at answer choice B, I've already said that glucose and fructose, and this is friendly of them, okay, because they made you look at the molecular formula in the previous question of glucose and fructose. That means you knew, because of your experience with the previous question, because you knew from your experience with the previous question that glucose was and fructose was C6H12O6. You knew that. That's how you knew that they were isomers of each other. And so you knew that the empirical formula for both glucose and fructose was CH2O. So now you're looking at these other guys, and glyceraldehyde molecule we looked at before, and it's one of the simplest carbohydrates. It's a triose. It has 3 carbons, and it's C3. If you count it up, C3H6O3. Oh. Yeah, O3. So you can't make that any lower. You can't do anything about that, right? Can we divide that by something? Yeah, we can. Yes, we can. We can divide it by 3. And if we divide it by 3, we get CH2O. There we go, carbohydrate, they're the same. So they have the same empirical formula. And let me take a look quickly at the other ones. I'm sure you can work out the other ones, but I just want to Make sure you have it for posterity. Oxalosuccinic acid is C6H12. 6, no, C6H6. Or 7. So that's not divisible by anything. And then as you can see, we have fumaric acid, which is and oxygen 4. And so that's equal to CHO as a empirical formula, and so that's clearly different. And then for D, we have the same C6H6O7, and that's versus oxaloacetic acid, which is C4, for hydrogens and oxygens, got 5. So there you go, and that's not reducible, and the other one is not reducible. No, it's not reducible to its simplest whole number, and so we're stuck with that, and so it's answer choice B is the only one where both have the same thing. So, I mean, you know, what are they asking you to do here? They're asking you to be fast, because you have to be quick with this so that you have time for other questions. Because other than that, there's not much, thinking here. Question number 38. Does ask you about a reaction. So the reaction results in producing malic acid. So as I told you before, you know, when you think of a reduction reaction, think about adding hydrogens or removing oxygen. You should write that. If you have a paper in front of you, write that down. And while you watch the video later on the website, an oxidation reaction means removing hydrogens or adding oxygen. So let me look at the reaction making malic acid from fumaric acid. Okay, so let's just write a little bit what that reaction means. Okay, so there's the reaction. We have fumaric acid on the left-hand side, and it's making malic acid on the right-hand side. And hopefully you can just see what's missing here. And what's missing is there's 2 hydrogens missing on the left side, and there is 1 oxygen missing on the left side. So that means we should put some water on the left side. Just, you know, I don't know if X is on the left or on the right-hand side. I don't. But I'm just looking at fumaric acid on the left, and I'm looking at malic acid on the right, and I'm looking at the difference, and I see that something must have been added to fumaric acid in order to make malic acid, and that something is exactly H2O. Now we have to know what adding H2O means, because if you add water to something, of course it's hydration. You know, when you add water to yourself, you say, I'm hydrating myself. Or if you don't have water, you're dehydrated. And so you know that adding water is hydration. And so this looks like hydration, but we have to figure out this hydrolysis thing. What is that? Because hydro, it also has hydro, which is water, but it has lysis in it. And lysis in biology and chemistry generally means break apart. So it breaks something apart. Hydrolysis or hydrolysis is when water is added and then the chemical breaks into 2. And we've seen it. We've seen hydrolysis or hydrolysis because it's the opposite of condensation reactions, and we looked at the condensation reactions for way back here. When we were talking about, you know, 2 monomers, 2 monosaccharides combining to make a disaccharide, that's called condensation. Water is released. The reverse reaction is hydrolysis, where water is added to the disaccharide and breaks it apart into two monosaccharides. So that's hydrolysis, hydrolysing, water breaking something apart. So here we just have hydration, so water being added, and it's not a bad thing to look at this reaction. Is it fumaric acid, malic acid, fumaric acid, fumaric and malic? Yes, it's not a bad reaction. It's kind of, don't worry, we're almost done. But this kind of reaction, you're sort of expected to know that this kind of thing can happen. So I'm going to try to draw it. When optimism hits reality. Oh, I've got something for you to do while I'm doing this. Give the systematic name of this compound. Please don't say fumaric acid. Wow, nobody guessed. So this compound, it's diacid. It's got two carboxylic acid groups. It's also, it's got 4 carbons, as you can see. Let me get the pointer. Yeah, so you have 4 carbons. It's a diacid, and yeah. So what we have here is butene. Okay, so but means 4 carbons. So butene, dioic acid, butene dioic acid, di, because there's 2 carboxylic acid groups. So it's, and if you want to be really fancy, you'd say this is trans, right? Because they're on opposite sides of the double bond. If you wanted to be even better, you'd say it's E, because they're on opposite sides of the double bond. So it would be an E for trans. 2 butene dioic acid. And it's obviously an unsaturated acid because carbon is not bonded to the maximum number it could be bonded to. So delta negative oxygen hits delta positive carbon, electrons go over here, and then the hydrogen adds here. So OH group adds here, hydrogen adds there, boom, it's all done. So water adds to this. The molecule does not break apart. Breaking apart would be hydrolysis. It's only water adding to the molecule. So that's why answer choice is a hydration reaction. Question number 39, the final question for organic chemistry. We made it. So a new artificial sweetener, replace all hydroxyl groups attached to ring carbon with chlorine. So back to glucose, one of the most important molecules known to mankind. Yes, DNA is important. Glucose is on the short list. So we have, again, C6, 6H. So, 6. So, I mean, in 3 different questions, we've had to deal with the molecular formula of glucose. So hopefully you're comfortable writing that at this point. The carbohydrate, CH2O. So what do we need to do with this? We need to replace all hydroxyl groups directly, they said directly attached to the ring. So then we look at the molecule. We look at how many hydroxyl groups are directly attached to the ring. We can 1, 2, 3, 4 hydroxyl groups. because there is another hydroxyl group, but it's not directly attached to the ring. It's attached to a CH2 group, which is attached to the ring. So 4 OH groups we are going to remove. So let's do that. Minus 4 OH. And what are we left with? So same number of carbons. We have C6 carbons. We minus 4 hydrogens. So we have H8 hydrogens. We subtracted 4 oxygens. So we have O2. Okay. And just trying to remember, we removed 4 ligands, and ligands, which are substituents or groups attached. We removed 4 OH ligands. So that means we must add 4 ligands to replace those positions. And we are told to add the appropriate amount of chlorine. So we have to add 4 chlorine ions to replace the 4 OH groups. So now that's our molecular formula, but they're not asking for the molecular formula. And it would be very bad if you saw this and answered it there, because they're asking for the empirical formula. So now we take that, we find the lowest common number, which is the number 2 on the oxygen. So then we can turn the carbon to 3, we turn the hydrogen to 4, because we're dividing by 2. The oxygen will be 1. The chlorine divided by, the 4 divided by 2 will be 2. So chlorine will be 2. And the oxygen is 1. And there's no reason that I'm putting it at the end, other than that's what ACER has done. So I'm putting the oxygen at the end. There we go. Okay, so now we have a empirical formula for the chlorinated glucose with the substituents changed to chlorine. And this is the empirical formula, and you also see above the molecular formula. And that's it. So if you are having problems with the molecular or empirical formulas, you can look at it in Chem 1.2 in the book. If you're looking for isomers, different isomers, or 2.1 and 2.2, we talked about some isomers, structural and stereoisomers. And for metabolism, which would not help you get anything right here, but it just gives you some background information on glycolysis and Krebs cycle and phosphorylation and so on, and that's in Bio 4.4 and 4.5.